Note, based on this theorem, we can see that for any matrix, the dimension of the column space is the same as the number of columns that contains leading ones in the reduced Rorschach form of the matrix. The dimension of a column space is the same as the number of columns that contains leading ones in the reduced Rorschach form of the matrix. So, for any matrix, the dimension of the column space is the same as the number of columns that contain leading ones in the reduced Rorschach form of matrix A. That's the same as the number of leading ones in the reduced Rorschach form of matrix A. That's the same as the number of leading ones in the reduced Rorschach form of matrix A. And according to the previous theorem, we know that the dimension of the row space is the same as the number of non-zero rows in the reduced Rorschach form of matrix A. According to this theorem, we know that the dimension of the row space is the number of non-zero rows in the reduced Rorschach form of the matrix. The dimension of the row space is the number of non-zero rows in the reduced Rorschach form of matrix A. And we know that for each non-zero row, it contains a leading one. For each non-zero row, it contains a leading one. So that's also the same as the number of leading ones in the reduced Rorschach form of matrix A. Since for each non-zero row, it contains a leading one, the dimension of the row space is also the same as the number of leading ones in the reduced Rorschach form of matrix A. Therefore, here we can see that for any matrix, the dimension of a column space is always the same as the dimension of the row space. For any matrix, the dimension of the column space is always the same as the dimension of the row space. Also, according to a previous theorem, we know that the dimension of the null space is always the number of columns without leading ones in the reduced Rorschach form of matrix A. Also, we know that the dimension of the null space for any matrix, the dimension of the null space is the number of columns that do not contain the leading one. Number of columns that do not contain leading ones in the reduced echelon form of matrix A. Here we can see that for any matrix, the dimension of the column space is always the same as the number of columns that contain leading ones in the reduced echelon form. And the dimension of the null space is the number of columns that do not contain leading ones in the reduced echelon form. Therefore, the dimension of the column space plus the dimension of the null space is the same as the total number of columns in matrix A. Since in the reduced echelon form, the dimension of matrix A stays the same, and each column it either contains the leading one or it does not contain the leading one. And the dimension of column space is the number of columns that contains leading one. Dimension of the null space is the number of columns that do not contain leading ones. Therefore, if I add them together, that's the total number of columns in matrix A. So, based on this, we have the following theorem. Theorem. Let A be an m by m matrix. Then we know that the dimension of its row space is always the same as the dimension of its column space. And the dimension of its column space plus the dimension of its null space is the same as the number of columns in matrix A. Here, A is a m by m matrix. That means A has m rows and m columns. So dimension of column space plus dimension of null space must be n, the number of columns in matrix A. That's the relationship between the row space, column space, and the null space. This theorem is very, very important. Keep this theorem in mind. Next, let's look at an example. Let A be a 3 by 5 matrix. Find the basis of its row space, column space, and null space. Let's find the basis for its row space and column space first. In order to find the basis for the row space and column space, we must reduce matrix A to the reduced echelon form. Here, matrix A is 1, -2, 1, 3, 1, 1, -2, 2, 5, 0, -2, 4, 3, 4, -7. Let's reduce the matrix first. In the first row, this is a leading one. We try to make all entries below leading one to be 0. So I can multiply first row by -1, add it to the second row. First row stays the same. I get 1, -2, 1, 3, 1. Multiply first row by -1, add it to the second row. I get 0, 0, 1, 2, -1. Next, I multiply first row by 2, add it to the third row. I get 0, 0, 5, 10, -5. Next, in the second row, try to make the first non-zero entry to be a 1. It is a 1 here. So that's a leading one in the second row. We try to make all entries above and below leading one to be 0. So here I can multiply second row by -1, add it to the first row. I get 1, -2, 0, 1, 2. Second row stays the same. I get 0, 0, 1, 2, -1. Next, I can multiply second row by -5, add it to the third row. I get 0, 0, 0, 0, 0. That's the reduced Rotron form of matrix A. Next, according to earlier theorem, we know that the basis of a row space is formed by all non-zero row vectors in the reduced Rotron form. So for the basis of the row space, it's formed by all non-zero row vectors in the reduced Rotron form. We have 1, -2, 0, 1, 2, and 0, 0, 1, 2, -1. That's the basis of the row space. Next, for the basis of the column space, according to earlier theorem, we know that for the basis of column space, we first of all find the leading ones in the reduced Rotron form. Here we have leading ones in the first column and the third column. Then, for the basis of the column space is formed by the original column vectors in the same places. The basis of the column space is formed by the original column vectors in the same places, which is the column vector in the first column and the third column. So for the basis of the column space, it contains two vectors, 1, 1, -2, and 1, 2, 3. That's the basis of the column space. Here we can see that the dimension of a row space is 2, since there are two vectors in the basis. And the dimension of column space is also 2, since there are two vectors in the column space. Let's match this theorem. The dimension of a row space is always the same as the dimension of a column space. Next, we try to find the dimension of a null space. For the dimension of null space, we first of all set AS equal to 0. For dimension of null space, we first of all set AS equal to 0. Then, the augmented matrix of this equation. For the augmented matrix of this equation, I first of all copy matrix A here. Matrix A is 1, -2, 1, 3, 1, 1, -2, 2, 5, 0, -2, 4, 3, 4, -7, and then set each row equal to 0. Set each row equal to 0. Then use Gauss-Jordan elimination. Reduce this matrix to the reduced echelon form. Apply Gauss-Jordan elimination. And we know that the reduced echelon form of matrix A is this. Last column is 0, it stays the same. So use Gauss-Jordan elimination, we get the same matrix here, followed by a column of zeros. We get 1, -2, 0, 1, 2, followed by a 0 in the first row. 0, 0, 1, 2, -1, followed by a 0 in the second row. 0, 0, 0, 0, 0, followed by a 0 in the third row. That's the reduced echelon form of this matrix. Next, rerun this matrix back to equations. Rerun this matrix back to equations. The first row can be rewritten as S1 minus 2S2 plus X4 plus 2S5 equal to 0. The second row can be written as X3 plus 2S4 minus S5. Here, since S1 and X3 they are leading variables, we try to isolate S1 and S3. So I get S1 equal to 2S2 minus S4 minus 2S5. In the second equation, I get x3 equal to negative 2S4 minus plus S5. Next, put S1, S2, S3, S5 in columns. Next, put S1, S2, S3, S4, S5 in columns. Since x2, S4, S5, they are free variables, we pick variable for x2, S4, S5. So let S2 equal to T, let S4 equal to S, let S5 equal to R. Here, S1 is 2S2 minus S4 minus 2S5, which is 2T minus S minus 2R. S2 is T. S3 is negative 2S4 plus S5, which is negative 2S plus R. Negative 2S4 plus S5. S4 is S. S5 is R. Here we have three variables, R, S, T. So put T in a column, S in a column, and R in another column. First column I have 2T, T, 0, 0, 0. Second column I have negative S, 0, negative 2S, S, 0. In the third column, I have negative 2R, 0, R, 0, R. Next, I can pull out T, pull out S, pull out R. If I pull out T, I get 2, 1, 0, 0, 0. If I pull out S, I get negative 1, 0, negative 2, 1, 0. If I pull out R, I get negative 2, 0, 1, 0, 1. Then, for the null space, we know that these three vectors form a basis of the null space. So the basis of the null space is formed by these three vectors. We write these three vectors in comma delimited form. That's 2, 1, 0, 0, 0. Negative 1, 0, negative 2, 1, 0. Negative 2, 0, 1, 0, 1. That's the basis of the null space. And since there are three vectors in the basis, we know that the dimension of the null space is 3. The dimension of null space is 3. Since the dimension of the column space is 2, dimension of null space is 3. When I add them up, I get 5, which is the same as number of columns in matrix A. 2 plus 3 is 5, which is the same as number of columns in matrix A. Let's match this theorem here. The dimension of the column space plus the dimension of the null space equal to number of columns in matrix A. Next, in the previous example, we know that the column vectors C2, C4, and C5, they are not in the basis of the column space. In the previous example, C2, C4, C5, they are not in the basis of the column space. Only C1 and C3 they are in the basis of the column space. Write C2, C4, C5 as linear combinations of C1 and C3. What should we do here? Let's first of all try to write C2 as a linear combination of C1 and C3. So I first of all set K1, C1 plus K3 C3 equal to C2. Then the augmented matrix of this vector equation can be written as, I put C1 in the first column, C3 in the second column, and C2 in the last column. The component of C1 is 1, 1, negative 2. Component of C3 is 1, 2, 3. Component of C2 is negative 2, negative 2, and 4. Next, we reduce this matrix, perform the same operations as we reduce matrix A. For this matrix, perform the same operations as we reduce matrix A. So here, perform the same operations. As reducing matrix A. If we perform the same operations, the first column here is 1, 1, negative 2. That's the same as the first column in matrix A, 1, 1, negative 2. If we reduce it, it becomes 1, 0, 0. Second column is 1, 2, 3, which is the same as the third column in matrix A. If we reduce it, we get 0, 1, 0. The third column is negative 2, negative 2, 4. Negative 2, negative 2, 4, that's the same as the second column in matrix A. If we reduce it using the same operation, we get negative 2, 0, 0. This matrix is in the reduced echelon form. The first row says K1 equal to negative 2. The second row says K3 equal to 0. That means C2 equal to negative 2 times C1 plus 0 times C3. And we know that 0 times C3 is 0. We can remove this 0 here. So here, C2 is negative 2 times C1. We write C2 as a linear combination of C1 and C3. Next, we shall write C4 as a linear combination of C1 and C3. So next, I set K1 C1 plus K3 C3 equal to C4. Then, for this vector equation, its augmented matrix looks like this. I put C1 in the first column, C3 in the second column, and then component of C4 in the last column. C1 is the first row vector here in matrix A, 1, 1, negative 2. C3 is the third row vector, it's the third column vector in matrix A. C1 is the first column vector in matrix A. C3 is the third column vector in matrix A. That's 1, 2, 3. C4 is the fourth column vector in matrix A. That's 3, 5, 4. Next, we reduce this matrix using the same operation as we reduce matrix A to the reduced echelon form. Reduce the matrix using the same operation as we reduce A to its reduced echelon form. So perform the same operations as reducing A. What do we get here? If we perform the same operations, the first column is 1, 1, negative 2. That's the same as the first column in matrix A, 1, 1, negative 2. If we reduce it using the same operation, we get 1, 0, 0. The second column is 1, 2, 3. That's the same as the third column in matrix A, 1, 2, 3. If we reduce the matrix using the same operation, I get 0, 1, 0. The third column is 3, 5, 4. That's the same as the fourth column in matrix A, 3, 5, 4. If we reduce the matrix using the same operation, we get 1, 2, 0. This matrix is in the reduced echelon form. Based on this matrix, we can see that here, K1 equal to 1, K3 equal to 2, K3 equal to 2. Second scalar is K3, K3 equal to 2. That means C4 can be written as 1 times C1 plus 2 times C3. Here I write C4 as a linear combination of C1 and C3. Next, we try to write C5 as a linear combination of C1 and C3. So in order to write C4 as a linear combination of C1 and C3, we set K1 C1 plus K3 C3 equal to C5. Then the augmented matrix for this vector equation can be written as a matrix with C1 in the first column, C3 in the second column, and C5 in the last column. C1 represents the first column vector in matrix A, which is 1, 1, negative 2. C3 is the second column vector. Is the third column. C3 is the third column vector in matrix A. That's 1, 2, 3. C5 is the fifth column vector in matrix A. That's 1, 0, negative 7. Next, we reduce this matrix. For this matrix, we perform the same operations as we reduce matrix A to its reduced echelon form. We perform the same operations as we reduce A to its reduced echelon form. Next, perform the same operations as reducing matrix A. First column 1, 1, negative 2. That's the same as the first column in matrix A, 1, 1, negative 2. If I reduce the matrix using the same operation, I get 1, 0, 0. Second column is 1, 2, 3. That's the third column in matrix A. If we reduce the matrix using the same operations, eventually I get 0, 1, 0. Last column is 1, 0, negative 7. That's the fifth column in matrix A. If we reduce the matrix using the same operation, we get negative 2, 1, 0. So you get 2, negative 1, 0. 2, negative 1, 0. This matrix is in the reduced echelon form. Based on this matrix, we can see that here, K1 equal to 2, and K3, the second scalar is K3, K3 equal to negative 1. So C5 can be written as 2 times C1 minus 1 times C3. Here I write C5 as a linear combination of C1 and C3. Next, in the previous example, find a basis of a row space which contains only the original row vectors. In the previous example, in a basis of a row space, it contains two vectors. These two vectors, they are not the same as the original row vectors in matrix A. They are not the same as the original row vectors in matrix A. In these examples, we try to find a basis of a row space which contains only the original row vectors in matrix A. So, in order to find a basis that contains only the original row vectors, we treat each row vectors as column vectors. We first of all treat each row vectors as a column vectors. So, the row space in the previous example the row space is spanned by these three vectors. R1 is 1, -2, 1, 3, 1. R2 is 1, -2, 2, 5, 0. R3 is -2, 4, 3, 4, -7. So the row space is spanned by these three row vectors. In order to find a basis that contains only the original row vectors, we treat each vector as a column vector. So I form a matrix which treat each row vectors as column vector. So the first column is R1, 1, -2, 1, 3, 1. We treat R1 as the first column vector. Next, I treat R2 as the second column vector. 1, -2, 2, 5, 0. Next, I treat R3 as the third column vector. I get -2, 4, 3, 4, -7. Next, reduce this matrix to the reduced echelon form. In the first row, there's a leading one here. I try to make all entries below leading one to be 0. So I can first of all multiply first row by 2, add it to the second row. First row stays the same. I get 1, 1, -2. Multiply first row by 2, add it to the second row. I get 0, 0, 0. Next, there's a leading one here. There's a leading one here. I try to make 0 here. So I multiply first row by -1, add it to the third row. I get 0, 1, and 5. Next, in the fourth row, try to make 0 here. So I multiply first row by -3, add it to the fourth row. I get 0, 2, and 10. Next, there's a 1 here. I try to make 0. So I multiply first row by -1, add it to the fifth row. I get 0, -1, and -5. Next, in the second row, try to make the first non-zero entry to be a leading one. That's impossible here. So I need to move. I need to interchange the second row and the third row. Next, interchange the second row and the third row. First row stays the same. I get 1, 1, -2. Second row is 0, 1, 5. Third row is 0, 0, 0. Fourth row stays the same. Fifth row stays the same. There's a leading one here. I try to make all entries above and below leading one to be 0. I can first of all multiply second row by -1, add it to the first row. It's 1, 0, -7. Then leave second row the same. 0, 1, 5. Leave the third row the same. It's already a 0 here. Leave the third row the same. Next, I try to make 0 here. I can multiply second row by -2. Add it to the fourth row. I get 0, 0, 0. Next, in the fifth row, try to make 0 here. I can directly add a second row to the fifth row. I get 0, 0, 0. That's the matrix in the reduced echelon form. Then, in order to find a basis that contains the original row vectors, I first of all find the leading ones. in the reduced echelon form. I have a leading one in the first column and the second column. Then, according to earlier theorem, we know that the original column vectors in the same place, form a basis of the column space, which is our row space here. So the basis of the above row space contains two vectors. The vector in the first column and the second column. 1, -2, 1, 3, 1, and 1, -2, 2, 5, 0. That's the basis of the row space. And it contains the original row vectors. It contains only the original row vectors. Next example, let v1 and v2 be two vectors, and let S be the set of v1 and v2, which is linearly independent. You can verify by yourself. Let v1 and v2, they are linearly independent vectors. You can verify by yourself. Enlarge S to a basis of R4. We know that R4 has dimension 4, so all its bases must have 4 vectors. In S, there are only 2 vectors. So in this problem, we try to find 2 more vectors added to S to form a basis of R4. In order to find 2 more vectors, I first of all treat v1 and v2 as row vectors. Put this vector in rows. So here I put v1 in the first row. I get 1, 2, 3, 4. And put v2 in the second row. I get -2, -4, 1, 6. Next, reduce this matrix to the reduced echelon form. So I can first of all make leading one in the first row. This is a leading one. So I multiply first row by 2, add it to the second row. I get 1, 2, 3, 4 in the first row. Multiply first row by 2, add it to the second row. I get 0, 0, 7, 14. Next, in the second row, we try to make the first non-zero entry to be a 1. So I can divide second row by 7. Next, I divide second row by 7. So first row stays the same. I get 1, 2, 3, 4. Second row is 0, 0, 1, 2. Next, let the leading one in the second row. I try to make all entries above or below leading one to be 0. So I try to make 0 here. Next, I multiply second row by -3, add it to the first row. So first row is 1, 2, 0, -2. Second row stays the same, 0, 0, 1, 2. That's the reduced echelon form. Of this matrix. Next, based on this matrix, we try to find 2 more vectors in R4 and add it to S to form a basis in R4. Now, what vectors should we add to S to form a basis? We know that the standard basis of R4 is what? The standard basis in R4 has 4 vectors. E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. And E4 is 0, 0, 0, 1. We try to find 2 vectors from here and add it to S to form a basis in R4. In this matrix here, we have leading one in the first component and in the third component. We are missing a leading one in the second component and the fourth component. Here, E2 has leading one in the second component, and E4 has leading one in the fourth component. So I will add these 2 vectors to S to form a basis in R4. So next, I add these two vectors to S. Let me call this vector V3. Let me call this vector V4. At V3, which is 0, 1, 0, 0. At V3 and V4, 0, 0, 0, 1 to S. Here I call this vector V3 and call this vector V4. Add these two vectors to S. Then, if I treat these vectors as V1, V2, V3, V4 as row vectors, I have V1 in the first row, 1, 2, 3, 4. V2 is in the second row, -2, -4, 1, 6. V3 in the third row, 0, 1, 0, 0. V4 is 0, 0, 0, 1. If I treat these vectors, V1, V2, V3, V4 as row vectors, I get this matrix. Next, if I perform the same operation here, if I perform the same operation as an above matrices, if I perform the same operation as an above matrices, in the above matrix, there's only two rows. So if I perform these operations, I only change the first two rows. The third row and the fourth row stays the same. Since this matrix has only two rows, if I perform the same operation here, I only change the second row and I only change the first row and the second row. The third row and the fourth row stays the same. So the third row and the fourth row stays the same. I only change the first row and the second row. If I perform the same operation, first row become 1, 2, 0, -2. Second row become 0, 0, 1, 2. Next, I can interchange row 2 and row 3. I get 1, 2, 0, -2. 0, 1, 0, 0. 0, 0, 1, 2. 0, 0, 0, 1. Now that's a leading one in the second row. I can multiply second row by -2, add it to the first row to make 0 here. I get 1, 2, 0, -2. 1, 0, 0, -2. 0, 1, 0, 0, 0, 0, 1, 2. 0, 0, 0, 1. That's a leading one in the first row. I can multiply the fourth row by 2, add it to the first row to make 0 here. Then multiply the fourth row by -2, add it to the second row to make 0, add it to the third row to make 0 here. Next, I multiply the fourth row by 2, add it to the first row. I get 1, 0, 0, 0. 0, 1, 0, 0. Next, I can multiply the fourth row by -2. Add it to the third row. I make 0, 0, 1, 0. The fourth row stays the same. I get 0, 0, 0, 1. That's the reduced rational form of this matrix. That's the reduced rational form of this matrix. Then, by earlier theorem, we know that doing row operations, doing elementary row operations, won't change the row space. Performing elementary row operations won't change the row space. So according to earlier theorem, we know that span of span of these 4 row vectors. Span of these 4 row vectors. v1, v2, v3, v4 is the same as the span of these 4 row vectors. And these 4 row vectors, they are e1, e2, e3, e4. Since e1, e2, e3, e4, they are the standard basis in R4. Since this is the standard basis in R4, the span of the standard basis equal to R4. The span of the standard basis equal to R4. Those are the standard bases in R4. The span of the standard basis equal to R4, which means the span of these 4 vectors v1, v2, v3, v4 is R4. Since span of v1, v2, v3, v4 equal to R4, and R4 has dimension 4. Then, if a set has 4 vectors, it spans R4, then these 4 vectors must be linearly independent. Therefore, it's a basis in R4. If a set of 4 vectors spans R4, then these 4 vectors must be linearly independent. Therefore, these 4 vectors is a basis of R4. Hence, v1, v2, v3, v4 is a basis in R4. That's how we enlarge S to be a basis of R4. I add 2 more vectors to S to form a basis in R4. That's how we enlarge S to a basis of R4. Next example, let v1, v2, v3, v4, v5 be 5 vectors, and let S be the set of v1, v2, v3, v4, v5, which is linearly dependent. Here you can verify by yourself. These vectors, v1, v2, v3, v4, v5, they are linearly dependent vectors. You can verify by yourself. Find a linearly independent subset of S called T, such that span of T equal to span of S. So here, since S is linearly dependent, we try to remove some vector from S to form a linearly independent subset of S. But the span of T is the same as span of S. Now, what vector should we remove from here? What vector should we remove from S to form a linearly independent subset? So in order to decide what to remove, we treat these vectors v1, v2, v3, v4, v5 as column vectors. In order to decide what to remove, we treat these vectors v1, v2, v3, v4, v5 as column vectors. Put v1 in the first column, v2 in the second column, v3 in the third column, v4 in the fourth column, v5 in the last column. Next, reduce this matrix to the reduced low echelon form. Reduce this matrix to the reduced low echelon form. So in the first row, that's a leading one here. we try to make all entries below leading 1 to be 0. So here I can multiply first row by -2, add it to the second row. So first row stays the same. I get 1, -2, 1, 0, 0. Multiply first row by -2, add it to the second row. I get 0, 0, -1, 1, 1. Next, I can multiply first row by -3, add it to the third row. I get 0, 0, -2, 2, 0. Next, I can multiply first row by -4, add it to the fourth row. I get 0, 0, -3, 3, and -1. Next, move to the second row. Try to make the first non-zero entry to be a leading one. What I can do here is I can multiply second row by -1. I can multiply second row by -1. So first row stays the same. I get 1, -2, 1, 0, 0. Multiply second row by -1. I get 0, 0, 1, -1, -1. The rest stays the same. Now in the second row, there's a leading one here. We try to make all entries above and below leading one to be 0. What I can do here is I can multiply second row by -1, add it to the first row. I get 1, -2, 0, 1, 1. Second row stays the same. I get 0, 0, 1, -1, -1. Next, I can multiply second row by 2, add it to the third row. I get 0, 0, 0, 0, -2. Next, I can multiply second row by 3, add it to the third row. Add it to the fourth row. I get 0, 0, 0, 0, -3 plus -1 is -4. Next, in the third row, try to make the first non-zero entry to be a 1 here. I can divide the third row by -2. So -1/2 times R3 times row 3. I get 1, first row stays the same. 1, -2, 0, 1, 1. Second row stays the same. 0, 0, 1, -1, -1. Third row is 0, 0, 0, 0, 1. Fourth row stays the same. I get 0, 0, 0, 0, 1, -4. Next, there's a leading one in the third row. I try to make all entries above and below leading one to be 0. So next, I can multiply the third row by -1, add it to the first row. I get 1, -2, 0, 1, 0. Next, I can directly add a third row to the second row. I get 0, 0, 1, -1, 0. Next, I can multiply the third row by 4, add it to the fourth row. Third row stays the same. I get 0, 0, 0, 0, 1. Fourth row here becomes 0, 0, 0, 0, 0. That's the reduced Rorschach form of this matrix. And by an earlier theorem, we know that we have leading ones in the first column, second column, and the third column. The original column vectors in the same place form a basis of the vectors of the column space. We have leading one here in the first column, third column, and the fifth column. According to earlier theorem, we know that the original column vectors in the same place form a basis of the column space. So these three vectors, form a basis of the column space, which means these three vectors, they are linearly independent and spans S, which is the column space. So these three vectors, they are linearly independent and they span S. So these three vectors, V1, V3, and V5, they are linearly independent. And these three vectors, V1, V2, V3, spans S. So we can simply let T be this set. Let T be the self V1, V3, V5. Then T is linearly independent, and span of T is the second span of S. Span of T equal to span of S. So I let T be the self V1, V2, V1, V3, V5. Here T is a subset of S, and T is linearly independent, and span of T is the same span of S. Next, in the previous example, write V2 and V4 as linear combinations of vectors in T. We know that in T there are three vectors, V1, V3, and V5. V2 and V4 are not belong to T. We try to write V2 and V4 as linear combinations of V1, V3, and V5. In order to write V2 as a linear combination of V1, V3, V5, I first of all set K1, V1 plus K3, V3 plus K5, V5 equal to V2. This is a vector equation. For its augmented matrix, I write a component of V1 in the first column. Component of V1 is 1, 2, 3, 4. Next, I write component of V3 in the second column. Component of V3 is 1, 1, 1, 1. Next, I write a component of V5 in the third column. Component of V5 is 0, 1, 0, -1. Next, put a component of V2 in the last column. Component of V2 is -2, -4, -6, -8. Next, reduce this matrix. Here, we'll perform the same operation as we reduce this matrix to the reduced Rotron form. So here, perform the same operations. As reducing the previous matrix. Here, perform the same operations as reducing the previous matrix. if I perform the same operations, the first column here is 1, 2, 3, 4, which is the same as the first column in the previous matrix, 1, 2, 3, 4. If we perform the same operation, the first column will become 1, 0, 0, 0. The second column here is 1, 1, 1, 1, which is the same as the third column in the previous matrix. If we perform exactly the same operations, the third column eventually becomes 0, 1, 0, 0. The third column here is 0, 1, 0, negative 1, which is the same as the fifth column in the previous matrix, 0, 1, 0, negative 1. If we perform exactly the same operation, the last column becomes 0, 0, 1, 0. And the last column here is negative 2, negative 4, negative 6, negative 8. That's exactly the same as the second column in the previous matrix. If we perform the same operations, the second column eventually becomes negative 2, 0, 0, 0, 0. This matrix is in the reduced restaurant form. This matrix is in the reduced restaurant form. So the first row says K1 equal to negative 2. Second row says K3 equal to 0. The third row says K5 equal to 0. Which means V2 equal to negative 2 times V1 plus 0 times V3 plus 0 times V5. So V2 equal to negative 2 times V1 plus 0 times V3 plus 0 times V5. Here I write V2 as the linear combinations of V1, V3, and V5. That can also be written as V2 equal to negative 2 times V1. Next, we should write V4 as the linear combinations of V1, V3, V5. So we set K1 V1 plus K3 V3 plus K5 V5 equal to V4. This is a vector equation. Its augmented matrix can be written as a matrix with V1 in the first column, V3 in the second column, V5 in the third column, and V4 in the last column. Component of V1 here is 1, 2, 3, 4. Component of V3 is 1, 1, 1, 1. Component of V5 is 0, 1, 0, negative 1. Component of V4 is 0, 1, 2, 3. Component of V4 is 0, 1, 2, 3. Next, we perform the same operation as we reduced the previous matrix. Perform exactly the same operation as we reduced the previous matrix. In this matrix, the first column match the first column in this matrix, 1, 2, 3, 4. If we perform exactly the same operations, eventually the first column becomes 1, 0, 0, 0. The second column is 1, 1, 1, 1, which match the third column in this matrix. If we perform exactly the same operation, the third column eventually becomes 0, 1, 0, 0. The third column here is 0, 1, 0, negative 1, which match the fifth column in the previous matrix. If we perform exactly the same operation, the fifth column becomes 0, 0, 1, 0. The last column here is 0, 1, 2, 3, which match the fourth column in the previous matrix. If we perform exactly the same operation, the fourth column becomes 1, -1, 0, 0. This matrix is in a reduced Rorschach form. This matrix is in a reduced Rorschach form. Based on this matrix, we can tell K1 equal to 1. Second scalar, K3 equal to -1. The third scalar, K5 equal to 0. So that means V4 equal to 1 times V1 plus -1 times V3 plus 0 times V5. So V4 equal to 1 times V1 plus -1 times V3 plus 0 times V5, which means V4 equal to V1 minus V3. Here I write V4 as a linear combination of V1, V3, and V5. Next, let me introduce kernel and range. Let A be an n by n matrix, and let T sub A from Rn to Rm be the matrix transformation associated to matrix A. Here, in this transformation, Rn is called a domain, Rm is called a codomain. The kernel and range of T sub A is defined as the following. The kernel of T sub A is in the set of all x in Rn in the domain, the set of all x in the domain, such that T sub A of x equal to 0. And the range of T sub A is the set of all b in the codomain. It's a set of all b in the codomain, such that b equal to T sub A of x for some x in the domain. That's how we define the kernel and range. Note, the kernel of the transformation T sub A is a subset of the domain. The kernel is a subset of the domain. The kernel is the set of all x in the domain, which is a subset of the domain. The range of T sub A is a subset of the codomain of T sub A. The range of T sub A is a set of all b in the codomain, such that b equal to T sub A of x for some x in the domain. So the range of T sub A is a subset of the codomain. So keep it in mind that the kernel is a subset of the domain, and the range is a subset of the codomain. Next, let's create a theorem. Let A be an n by n matrix, and let T sub A from Rn to Rm. Here, that's the domain, that's the codomain. Let T sub A from Rm to Rm be the matrix transformation associated to matrix A. Then, the kernel of T sub A, the kernel of the matrix transformation is the same as the null space of matrix A. The kernel of the transformation associated to A is the same as the null space of A. And the range of the transformation associated to A is the same as the column space of matrix A. The kernel of the transformation is the same as the null space. The range of the transformation is the same as the column space of A. Now let's prove it. Let's first of all prove that the kernel of T sub A is the same as the null space of A. In order to show two sets equal to each other, we must show that they are subsets of each other. We must show that the left side is a subset of right side, and the right side is a subset of left side. So first of all, I let x belong to the kernel of T sub A. First of all, I let x belong to the kernel of T sub A. I try to show that x also belongs to the null space of A. X belongs to the kernel of T sub A. That means T sub A of x equal to 0. So T sub A of x is the same as matrix A times x. If A times x equal to 0, that means x belongs to the null space of A. if for all x in the kernel of T sub A, x also belongs to the null space of A, that means the kernel is a subset of the null space. So the kernel is a subset of the null space. Next, we will show that the null space is a subset of the kernel. So next, I let X belong to the null space of A. Then if X belongs to the null space of A, that means A times X must be 0. And A times X can be rewritten as T sub A of X. If T sub A of X equal to 0, that means X belongs to the kernel of T sub A. If T sub A of X equal to 0, that means X belongs to the kernel of T sub A. Since every element in the null space of A is also an element of the kernel of T sub A, that means the null space is a subset of the kernel. If two sets they are subsets of each other, then they must be the same. If two sets are subsets of each other, then they must be the same. Therefore, the kernel of T sub A must be the same as the null space of matrix A. So the kernel of T sub A is the same as the null space of matrix A. Next, we shall prove that the range of T sub A is the same as the Kernel space of matrix A. First of all, let A be the matrix A11, A12. A has m rows and n columns. So the last entry in the first row will be A1n. Second row will be A21, A22, and A2n. Since A has m rows, the last row will be AM1, AM2, and AMN. In order to show two sets equal to each other, I want to show they are subsets of each other. So first of all, I try to show that the range of T sub A is a subset of the Kernel space of matrix A. So let B be an element of the range of T sub A. I try to show that this B also belongs to the Kernel space of matrix A. Since B belongs to the range of T sub A, that means there exists X in the domain such that B equal to AX, B equal to T sub A of X. That's the definition of range. There's X in the domain such that B equal to T sub A of X. Then B equal to T sub A of X. That can be rewritten as AX. Matrix A is this matrix. A11, A12, A1n in the first row. A21, A22, A2n in the second row. And AM1, AM2, AMN in the last row. X is an element in the domain. Here X belongs to Rn. that means X has n components. X has n components. So X will be x1, s2, up to Sn. Now, if I multiply, what do we get? If I multiply these two matrices, I use row times column, and then add them up. I get A11 S1 plus A12 X2 plus A1n Sn in the first row. Second row is A21 S1 plus A22 X2 plus A2n Sn, and continue. In the last row I have AM1 times S1 plus AM2 times S2 plus AMN times Sn. Next, I separate this matrix into columns. I put the first term in the first column, A11 times S1, A21 times S1. Continue. Last row is AM1 times S1. Second column is A12 times S2, A22 times S2. Continue. Last row is AM2 times S2 plus until the last column. Last column is A1n times Sn. A2n times Sn. And AMN times Sn. Next, on each column. In the first column I pour S1. On the second column I can pour S2. On the last column I pour Sn. I get S1 times the column vector A11, A21, AM1. It's S1 here. In the second column, pour S2. I get A12 times A22 times AM2. Continue in the last column. I pour out Sn. If I pour Sn, I get A1n, A2n, and AMN in the column. Those are column vectors. Those are column vectors in matrix A. Those are column vectors in matrix A. Since I can write B as a linear combination of column vectors in matrix A, that means B belongs to the column space of matrix A. Since I can write B as a linear combination of the column vectors in matrix A, that means B belongs to the column space of matrix A. So B belongs to the column space of matrix A. Since every element in the range of T sub A also belongs to the column space of matrix A, that means the range of T sub A is a subset of the column space of matrix A. So the range of T sub A is a subset of the column space of matrix A. Next, to show that the column space of A is a subset of the range of T sub A. Next, let B belong to the column space of A. We try to show that B also belongs to the range of T sub A. If B belongs to the column space of A, that means That means B can be written as a linear combinations of the column vectors in matrix A. Here, A has n columns, 1, 2, 3, up to n. A has n columns. B can be written as a linear combination of all column vectors in matrix A. So B equal to K1 times the first column. First column is A11, A21, and AM1, plus K2 times A12, A22, and AM2. Continue. A has n column vectors. Last column, last term is K sub n times A1n, A2n, and AMN. If B belongs to a column space of matrix A, B can be written as a linear combinations of all column vectors in matrix A. Those are the column vectors in matrix A. First column, second column, and nth column. Then, if I multiply the scalar of the columns, what do I get? I get A11 times K1, A21 times K1, AM1 times K1, plus A12 times K2, A22 times K2, and AM2 times K2, plus A1n times Kn, A2n times Kn, and AMN times Kn. Then I can add this column vector together. When I add the column vectors, I add the corresponding entries. So the first row is A11 K1 plus A12 K2 plus A1M Kn. Second row is A21 K1 plus A22 K2 plus A2n Kn. First row should be A1n Kn. In the last row, we have AM1 K1 plus AM2 K2 plus AMN Kn. This matrix can be rewritten as A11, A12, A1n, A21, A22, A2n. Last row is AM1, AM2, AMN times the column vectors K1, K2 up to Kn. This is matrix A. This is a column vector belong to Rn. This is a column vector belong to Rn, since it has n columns. Let me call this vector x. Then I can write B as A times x, where x belongs to Rn. And Ax can be written as T sub A times x. X belongs to Rn. Since I can write B as T sub A times x, that means B belongs to the range of T sub A. Since every element in the column space is an element of the range, That means the kernel space of A is a subset of range of A. So the kernel space of A is a subset of the range of T sub A. If two sets they are subsets of each other, they must be the same. Therefore, the range of T sub A is the same as the kernel space of A. So that's a proof of this theorem. Keep in mind that the kernel of the transformation is the same as the null space of A, and the range of the transformation is the same as the kernel space of A. Keep it in mind. Next theorem, let A be an m by n matrix, and let T sub A from Rn to Rm be the matrix transformation associated to A. Then, for the matrix transformation T sub A, the dimension of its kernel plus the dimension of its range is the same as the dimension of its domain. The proof of this theorem is straightforward from earlier theorem. From earlier theorem, we know that the dimension for any matrix A, the dimension of its kernel space plus the dimension of the null space is the same as n. N represents the number of columns. Here we know that the dimension of a kernel space, according to the previous theorem, we know that the dimension of a kernel space is the same as the dimension of the range. The dimension of the null space is the same as the dimension of the kernel. And n is the number of columns, which represent the dimension of the domain. N represents the number of columns, which is the same as the dimension of the domain. So the proof of this theorem is straightforward from the previous theorem here. Dimension of the kernel is the same as dimension of the null space. Dimension of the range is the same as the dimension of the kernel space. And n is the dimension of the domain. So the proof of this theorem is straightforward from the previous theorem, from earlier theorem here. So keep in mind that for any matrix transformation T sub A, the dimension of its kernel plus the dimension of its range is always the same as the dimension of the domain. Next, let me show you a theorem. Let A be a 4 by 3 matrix. Find the kernel and the range of T sub A. Here, T sub A is the matrix transformation associated to A. According to the earlier theorem, we know that the kernel of T sub A is the same as null space of A, and the range of T sub A is the same as the kernel space of matrix A. For this, find the null space and the kernel space of matrix A. Let's find the null space first. For null space, we first of all set AS equal to 0. Then, the augmented matrix of this equation can be written as matrix A 1, 2, -1, followed by the 0 in the first row, 0, 1, 1, followed by 0 in the second row, 2, 3, -3, followed by 0 in the third row, 2, 4, 4, followed by 0 in the last row. Then use Gauss-Schroeder elimination, reduce this matrix to the reduced echelon form. First of all, in the first row, that's a leading one. I try to make all entries below leading one to be 0. That's a 0. So I can first of all multiply the first row by -2, add it to the third row. I get 1, 2, -1, 0, 1, 1, 0, -1, -1. Last row stays the same. I get 0, 4, 4. Next, in the second row, that's a leading one here. So I can try to make all entries above and below leading 1 to be 0. Next, I can multiply the second row by -2 added to the first row. Multiply second row by -2 added to the first row. I get 1, 0, -3. Keep second row the same. I get 0, 1, 1. Next, I can add the second row to the third row. I get 0, 0, 0. Next, I can multiply the first row by -4. Multiply second row by -4. Add it to the fourth row. I get 0, 0, 0. Last column is 0. Now this matrix is in the reduced Rorschach form. I write it back as equation. First row says that S1 minus 3x3 is 0. Second row can be written as S2 plus x3 equals 0. Then here, the leading variable is S1, S2. X3 is a free variable. So next, get S1, S2 by itself. On the first equation, S1 can be written as 3x3. On the second equation, S2 can be rewritten as -x3. Since x3 is a free variable, we set s3 equal to t. Then S1, S2, x3 can be written as S1 equal to 3x3, that's 3t. S2 is -x3, which is -t. x3 is t, that's t. Then here there's only one variable. I can pull out t. If I pull out t, I get +3, -1, +1. That's the basis of the null space of matrix A. So, and we know that the kernel of T sub A is the same as the null space. So, the kernel of T sub A is the same as the null space, which is the span of this vector. Three, -1, and 1. That's the kernel of T sub A. Since the kernel is the same as the null space, that's the kernel of T sub A, which is the span of 3, -1, and 1. This is the basis of the null space. Next, that's for the range of T sub A. We know that the range of T sub A is the same as the column space of A. In order to find the column space, we reduce matrix A directly. Matrix A is 1, 2, -1, 0, 1, 1, 2, 3, -3, 0, 4, 4. Reduce matrix A to the reduced Rorschach form. Here we can perform the same operation, exactly the same operation. Perform exactly the same operation. I get 1, 0, -3, 0, 1, 1, and so on. Everything stays the same except the last column. Everything stays the same except the last column. So I get 1, 0, -3, 0, 1, 1, 0, 0, 0, 0, 0, 0. That's the reduced Rorschach form of this matrix. Next, we find the leading ones in the reduced Rorschach form. We have a leading one in the first column, a leading one in the second column. According to the earlier theorem, the original column vectors in the same place, in the first column and the second column form a basis of the column space. So these two vectors form a basis of the column space. And we know that the column space of A is the same as the range of T sub A. So the range of T sub A is the same as the column space of A, which is spanned by these two vectors. These two vectors is the basis of the column space. Spanned by these two vectors, 1, 0, 2, 0, 2, 1, 3, 4. That's the range of T sub A. And here we can check the previous theorem. We can verify the previous theorem. Previous theorem says the dimension of the kernel plus dimension of range equal to dimension of the domain. Here, for this matrix A, we can multiply this matrix by a 3 by 1 matrix. We can multiply this matrix by a 3 by 1 matrix, which means the domain of the transformation T sub A is R3. We can multiply this matrix by any 3 by 1 column vectors, which means the domain of T sub A is R3. So dimension of the domain is the same as dimension of R3, since domain is R3. And dimension of R3 is 3. And we know that dimension of the kernel here is 1. There's only one vector in the basis. There's only one vector in the basis. So dimension of the kernel is 1. And dimension of range, there are two vectors in the basis. That means dimension of the range is 2. Here we can verify that dimension of the kernel plus dimension of the range equal to dimension of the domain. That's how we verify the previous theorem. Next, let me introduce rank and nullity. For any matrix A, the dimension of the column space is called the rank of A, and the dimension of the null space is called the nullity of A. According to an earlier theorem, we know that for any matrix A, the dimension of the row space is the same as the dimension of the column space. Since the rank of A is the dimension of a column space, we can also say that rank of A is the dimension of the row space. So rank of A could be either the dimension of the row space or the dimension of the column space, because they are the same. Also, according to earlier theorem, we know that for any matrix A, the kernel of T sub A is always the same as the null space of A, and the range of T sub A is the same as the column space of A. By this theorem, we know that rank of A is the dimension of a column space. So we can also say that rank of A is the dimension of the range of T sub A. Also, since nullity of A is the dimension of the null space of A, we can also say that nullity of A is the dimension of the kernel of T sub A. So those are some properties about rank and nullity. Keep it in mind. Next, let me introduce a theorem called the dimension theorem of matrices. Let A be an m by m matrix. Then its nullity plus its rank equal to n. Here n is the number of columns. A is a m by m matrix, means A has m rows and n columns. The dimension theorem says nullity of A plus rank of A equal to the number of columns in matrix A. The proof of this theorem is straightforward. According to earlier theorem, we know that for any matrix A, the dimension of a column space plus the dimension of its null space equal to n. And we know that the dimension of a column space is rank of A. the dimension of a column space is rank of A. The dimension of null space is the nullity of A. So dimension of null space plus dimension of a column space equal to n. The proof of this theorem is straightforward from this theorem. So keep it in mind. Let's call the dimension theorem of matrices. For any matrix A, its nullity plus its rank equal to number of columns. And in the previous example, you can see that in this example here, the kernel of T sub A is the span of this one vector. That's the basis of the kernel, which means the dimension of the kernel is 1. Since the nullity of A is the same as the dimension of the kernel of T sub A, the nullity of A in this example, nullity of A is 1. Also, the range of T sub A is the span of these two vectors. These two vectors, they are basis of the range. These two vectors, they are basis of the range. Since there are two vectors in the basis of the range, the dimension of the range is 2. And we know that rank of A is the dimension of the range of T sub A, which means rank of A is 2. Since the dimension of the range is 2, we can say that rank of A is 2. So in this matrix A, nullity is 1, rank is 2. And this matrix A has 4 rows and 3 columns. So n equals 3. It satisfies the dimension theorem of matrices. Nullity is 1, rank is 2, n is 3. 1 plus 2 equals 3. Nullity is 1, rank is 2, and n equals 3. Since there are 3 columns, n equals 3. Nullity plus range. Nullity plus rank equal to n equals 3 here. It satisfies this dimension theorem of matrices. 1 plus 2 equals 3. Next theorem. For any matrix A, rank of matrix A is always the same as rank of A transpose. How can we prove it? We know that rank of A is the dimension of the column space of matrix A. So first of all, let A be a matrix with column vectors V1, V2, Vn. Let A be a matrix with column vectors V1, V2, Vn. Then A can be written as column vectors V1 in the first column, V2 in the second column, and so on. Vn in the last column. Let A be a matrix with column vectors V1, V2, Vn. Then what's A transpose? For A transpose, we put rows in columns, or we can put columns in rows. So for A transpose, the first row will be V1, second row will be V2, and continue, the last row will be Vn. That's A transpose. So let A be a matrix with column vectors V1, V2, Vn. Then the column vectors V1, V2, Vn, they are the row vectors of A transpose. They are the row vectors of A transpose. We know that rank of A is the dimension of a column space of A. Which is the same as the dimension of the span of the column vectors. The column vector here in A is V1, V2, Vn. for the column space is the span of the column vectors v1, v2, vn. So rank of A is the dimension of the span of these column vectors v1, v2, vn. Now, how about the rank of A transpose? Rank of A transpose, that's the dimension of the column space of A transpose. That's the dimension of the column space of A transpose. And according to earlier theorem, we know that for any matrix, the dimension of the row space is the same as the dimension of the column space. So the dimension of the column space of A transpose is the same as the dimension of the row space of A transpose. And the dimension of the row space of A transpose is the dimension of the span of these row vectors in A transpose. That's the dimension of the span of the row vectors in A transpose. In A transpose, the row vectors are v1, v2, vn. Here you can see that both rank of A and rank of A transpose equal to dimension of the span of these vectors v1, v2, vn. They both equal to the dimension of the span of these vectors v1, v2, vn. So rank of A equal to rank of A transpose. So rank of A equal to the rank of A transpose.